So this is a rather long lecture. It's Newton's first law of motion. We'll just get right into it. Prior to the 1600s, early scientists held a simplistic view of motion. They noticed that moving objects would spontaneously slow down for no apparent reason, and since they did not know about friction, they concluded that a constant net force was needed to keep an object moving. They thought, based on the teachings of Aristotle, that larger net forces made things move faster and smaller net forces made things move slower. Galileo questioned these. We talked about this in Unit 1. And he performed some real experiments with a ball rolling down some sloped ramps. And he did some virtual experiments as well, so kind of experiments of the mind to sort of explain these things as well. So Galileo reasoned that as a ball speeds up as it rolls down a slope, then it moves with a constant velocity along the horizontal surface, and then it rolls up that far slope from the same level it started. So what would happen here, if you dropped a ball at this height here, it would roll down. It would have constant velocity here, and it would roll up this ramp, slowing down and eventually stop at that spot. If the ramp was less steep, though, he found that the ball ends up essentially rising to the same spot, regardless of the size of this ramp. And then he further reasoned that if there was no ramp going up, then the ball would just go on forever. It wouldn't stop. There was nothing to slow it down. Of course, when he performed this experiment, then he observed that the ball rolling along the horizontal surface eventually stopped. However, he was able to assume correctly that the ball slowed down to zero velocity because of friction. So he determined that there was something that does stop it. It is the frictional force. Galileo concluded that once an object starts moving, it will continue moving at a constant velocity if there is no friction present. And he used the concept of inertia to explain this conclusion. Inertia is the property of matter that causes it to resist changes in its motion. The inertia of an object depends on the mass of the object. So inertia is a property of matter that causes it to resist changes in motion, and it's directionally proportional to the mass of an object. Since an object's mass is a measure of its inertia, and vice versa, there are many everyday examples of objects resisting a change in their motion. And here are some examples. When we have a car suddenly stop, a passenger in the front seat who might not be wearing a seatbelt would continue to move forward. They move forward because of their inertia. They could then collide with the windshield of the car, which could cause severe damage. You may have seen a magician kind of perform this type of magic trick where they pull a cloth out from under a place setting. Due to the inertia of the place setting, they might not move and stay where they are because it takes more to get them to start moving because of their mass. So by pulling that cloth out from underneath, the objects could stay where they are because of the inertia of the objects. Here's a parlor trick sometimes people would do where they place a card on top of a glass and a coin on top of the card, and you're asked to kind of get the coin inside of the glass. If you flick the card really fast, the card will move. The inertia of the coin will cause it to not to start its motion quick enough, and the coin will fall directly down into the glass. If you've ever had to get a stalled car moving, you may have noticed that you can kind of push forward on it, and it kind of sorts of pull back to sort of resist the motion. And you can push and pull back on the car using the car's own kind of inertia against it to get it to start moving again. So Newton's first law of motion is also called the law of inertia, and it's stated here as if the net external force on an object is zero, the object will remain at rest, or continue to move at a constant velocity. So we've already touched on this earlier when we talked about in our, I think it was our first or second lecture, where we talked about the net forces being zero. The law has several significant implications. So one of which is that objects at rest remain at rest unless acted upon by an external unbalanced force. So for example, a ball on a horizontal floor will remain at rest forever unless somebody gives it a push. Another implication, moving objects continue to move in a straight line at a constant speed unless acted upon by an external unbalanced force. So a car moving on a flat, icy curve, it tends to go in a straight line and fall off the road. Because of inertia, things tend to go in the same direction in which they were traveling. Another implication here is an external force is required to change the velocity of an object. Internal forces have no effect on an object's motion. For example, a passenger pushing on the dashboard of a car cannot change the velocity of the car. And if you're traveling in a car, there's nothing you can do inside the car short of actually touching the gas pedal to make that car move faster. Another implication here is that the external force must be unbalanced. That is, two equal opposing forces acting on an object will not change its velocity. For objects' velocity to change, the vector sum of the applied forces on the object must be a non-zero value. So here are some implications. Objects at rest tend to remain at rest. Objects at motion tend to remain in motion. Those are the two major ones. The others, if the velocity is constant, the net force acting on it must be zero. If the velocity is changing in direction or in magnitude, the change must be caused by an external net force acting on the object. Here are some questions just to think about. It says, older cars did not have headrests, but many new cars do. All new cars do, really. How do headrests prevent injuries? And use your Newton's first law to help explain this answer. Well, during a rear-end collision, you have your car sort of suddenly accelerating forward. This causes your head to kind of fall forward, and then your head whiplashes back. Well, whiplash is a serious neck injury. If you move your neck back really fast, really quickly, it could cause some damage to your neck. And in the older cars that didn't have headrests, people would tend to have whiplash from rear-end car accidents. The headrest prevents whiplash from occurring because your head ends up hitting the headrest, preventing you from bending your neck back too far. And here's a kind of an example, and you can read this slide on your own. That's a person there without a headrest, and that would cause a whiplash. Their neck would be bent back too much, too quickly, and that could cause damage. This question you won't really know the answer to, or you might, but I'll explain it using inertia. How does a seatbelt work? So if you've ever pulled on a seatbelt when somebody is slowing the car down quickly, you might notice that the seatbelt doesn't pull. That's because the seatbelt mechanism actually has a little pendulum underneath, and that pendulum has a certain inertia to it. When the car is quickly accelerating or quickly decelerating, it moves either to the left or to the right, and it causes it'll touch one of the gears of the seatbelt, preventing the seatbelt from moving. So if the car comes to a sudden stop, the seatbelt itself locks in place, and that holds a person still so that they don't move forward too much. Here's a slide to copy down some applications of Newton's first law. Headrests, seatbelts, airbags. There are going to be a few questions where you have to explain things, how physics is used to sort of make improvements in our lives, and Safety is a big one for these early units where we talk about motion and forces. And speaking of that, the next set of slides in this lecture talk about the interaction of science and technology. So this is an interesting topic because as things are learned in science, we can end up creating better technology. And then as technology increases, it could cause new problems that have to be solved using a scientific solution again. And then the new solution could cause another problem that wasn't foreseen before through the way people interact with the technology. So this kind of interaction between science and technology is interesting. We'll talk about it with airbags. So airbags, when they were first invented, they obviously caused, they prevented a lot of deaths from serious car accidents. But there were some other problems. Sometimes the airbags would cause injuries of their own. So let's just read here. It says, more problems are identified than as a result of the initial solution to the problem. The use of airbags caused injuries and deaths in certain instances. Thus, the process of scientific research starts again. So there was a need to find a way to solve this problem. So airbags prevented car accidents from being causing serious injury, but people were still being injured because of the airbags, because sometimes they were being deployed too quickly, or they would cause burns and scars on people's faces. So manufacturers are now testing airbags that can reduce injuries to pedestrians as well. They are similar to the interior airbags, but they would sense if a pedestrian is going to hit a car and then launch an airbag to sort of cushion the landing of the pedestrian. So here's a slide to copy down. It says, problem is identified, research and a solution is invented, the solution causes other problems, and the research begins again. This is the cycle of the interaction of science and technology. This question here, I'm not sure exactly why it was thrown in here, but it says, what is a virtual experiment? It is basically a thought experiment. Here it says, suppose you are helping a friend move and the friend asks you to stand in the back of a pickup truck to hold a piano because there's no rope available to tie it down. Why should you refuse this request? Well, because of inertia. If an object in motion tends to stay in motion, if you're in the back of a truck and something happens and he has to stop suddenly, you're going to be falling forward or falling backward if you get hit from behind or something. Why does a child on toboggan fall backward when the toboggan is given a sharp forward tug? So if a child is sitting on a toboggan and you pull the toboggan quickly forward, the child may fall backward because their inertia tends to try to keep them at rest. This one says, a friend carries their metal lunchbox on the ledge between the rear windshield and the rear seat of their car. How is that safe? Well, that metal lunchbox could quickly become a projectile inside the vehicle because any sort of sudden stop would cause that lunchbox to move forward because of the inertia of the lunchbox. And last question to look at here, it says, why must an object at rest have either no force or a minimum of 2 forces acting on it? An object at rest has to have a net force of 0. So if no force is acting on it, then you would have the object at rest and remaining at rest. If there was 1 force acting on it, well, then it would have to move because its net force would be a non-zero value. So there has to be at least 2 forces or no forces acting on an object for it to be at rest.